presented last week. So trying to implement a neural network a model that will differentiate between airplanes and birds. So we are just going to scan through this, and when there is the need to run any code, we will open the notebook on Colab to run some of the things. I have not set up the Colab because I am just in a hurry and I don't know why. But maybe we'll set it up together. I've opened it.
Do you have the Colab like the way you did it last time? You open them side by side so that when you don't need to.
Problem here is, we have some data paths to open, so I don't know whether, or maybe let me.
No, it's all right. Okay.
Mount my Google Drive so that I just go into the directory and then continue from there.
Session akan Google Colab din nan.
Yes, I don't think this is something different. It will be like
but I know it's not different. What I'm saying, what I'm saying, the concept of Google Colab, people from the beginning, like how they can start running machine learning in particular models. There are quite abuwa like mounting and then the Google some kind of stuff. So but Sani Baba made the presentation. The presentation. I don't know if we can use the opportunity discussion about Colab, how one can use Colab to do machine learning, maybe.
Yeah, so I separated the quotes from the mountain. So in the mountain, I think let's go into the directory so that if there is anything we are downloading directly, it goes into the deep learning with Pytorch directory. So since we are going one into data, that means we are going into this.
So kaga duk wannan abubuwan some of people here may not know how they can navigate all this kind of, so it's good idea maybe I think I suggest Kobe idan muka gama discussion din mu na normal house NLP, maybe session just few minutes, like 20 or 30 minutes, how to set up.
Okay, yes, Dr. Shamsu and others, I think why I like using Google Colab is most of the things are pre-installed already. So the little that maybe a person will have to install will just be dependent on what you are doing. So, but most of this Matplotlib, Pytorch, and everything is just installed already in Colab. So
idan kuma you have like such memory like mine, the way I don't like Colab is when I open it, I can see browsers, I can see tab, I just will open and start going to Google doing browsing. So my mind.
Yeah, so sometimes with even Colab, sometimes you get it's just like with programming. Sometimes you get you can't progress in one thing, so you just directly just open browser, search for that thing, and just come and implement it here. So sometimes that's the advantage with this. So
yeah, so when I open, normally before even like that, not Colab, even Jupyter, I don't like opening Jupyter in browser because it distracts me if I see tabs for browsing. So that's why I prefer for me to use something local. Yeah, so let's get started with it.
Yes. So now, the preface, is it preface they said is now we are using a data set, and the data set is called CIFAR. I think is let me see. Yeah, it's Canadian Institute for Advanced Research.
But it is what is the purpose of this chapter? What do we intend to get maybe after finishing this chapter on top of what we have seen?
So what we have seen before, I think, is implementing a neural machine model in the last chapter. So instead of so yeah, what we've been building before was the building blocks for for Pytorch. And then as at last week, we saw how to implement a real neural network. So now it's just an advancement. We are using image files to try to recognize. So it's basically it's a classification task, trying to recognize an image from a series of images. So yeah. So maybe if I explain the data set, and we will come to where, because the title of the chapter is trying to differentiate between planes and images, and we are going to see why we are doing that, because it's like you are a machine learning practitioner and somebody will come with a problem. So it's just that problem that came up, that a person wants to update her blog at every time a bird crosses through her field. But then there are many instances where aeroplane crosses the field and the images are like compiling a lot. So she wants the server to automatically detect whether it's a bird or a plane. If it is a bird, the image should be published to the blog, while if it is an aeroplane, the image should be deleted automatically. So she wants to automate the process. So there's the need for creating a classification model that tries to classify between a plane and a bird. So that's the essence here. But before going into that, we are going to see the data set, how to load the data set, and some kind of normalization that occurs on image data set that is like relevant to this task. Yeah. If you
go up this the chapter.
Now?
Can you go a little bit up the beginning of the chapter?
Okay.
Yeah, so here, yeah. So what I want to say here is this. What we have seen before is like we have data set. So one of the essence at the end of the chapter, we will understand something in Pytorch is called data set and data loaders. Yeah. So these are classes that allows you to load your data set into Pytorch. So you will see how previously we didn't see data sets and data loaders. So in this chapter, we'll see data set and data loaders, which are basically a kind of helpers that allow us to read any data set in Pytorch and even create a custom data set in Pytorch. Unlike where we used previously, like maybe read CSV to read your data, like we saw in, we know in what do we call it, in scikit-learn or machine learning. In Pytorch, we don't have that, not that read CSV like to create our data. So we use some classes called data set and data loader that can be used to automatically convert your data set into tensors. You saw previously we used tensors after we read our data set, but using these classes, data set and data loaders, you will just provide argument as you see to convert your, yeah. So that is one thing I want to say, that at the end of this session, we will be able to understand on top of what you said, data set and what is data loaders. Yeah, you can continue, Idris.
Okay. So, sorry, let me erase this. So thank you, Dr. Shamsu, for elaborating more. So what we are seeing here are a data set of tiny images, as I have said, is the Canadian Institute for Advanced, is it Advanced Research Artificial? Yeah, Advanced Research CIFAR. So the data set is named CIFAR 100. But we are going to see a smaller version of the data set, which is called CIFAR 10. And the meaning of this 10 and 100 is just the number of classes that we have in the image. So this CIFAR 10 have 10 classes, and the classes are named here in the pictures. So we have aeroplane, we have automobile, bird, cat, deer, dog, frog, horse, sheep, and truck. So these are the 10 classes that we have. So it consists of 60,000 tiny 32 by 32 color RGB images. And as we have seen in the basics, this 32 by 32 indicates the height and the width. And then the RGB is indicated in one dimension, the channel dimension, which is always 3 in images. So representing the red, the green, and the blue to show the color of the pixel at that, the color of each pixel. So, and this is the labeling. So now we are going to use Touch Vision to automatically download the data because I don't think we have the data. So to do the downloading, what we have, as Dr. Shamsu introduced, is the data set module. So the data set module enables us to load data set. Either if we have the data set in our local directory, we load it to start working with it, or if we don't have it, the data set automatically download the data. If you pass the argument download is equal to true. So if download is equal to false and you don't have the data set, it will tell you that the data is not available. But if download is true, it gives you the data set. If you also pass the train is true, it means that it is only going to download the train data and not the validation data. So that's why in this case, we instantiate a data set for training data by setting this parameter, train is equal to true. So if we are only downloading the validation set, we set the train is equal to false. So if we run this code, automatically it is going to download these two data sets, the training and the validation data set. So it's already splitted beforehand. So now let's run this code. So line, so that this will enable us to draw pictures. Yeah, matplotlib, and we initiate our class names. We all know them by this introduction. So let me see. No, I don't think we are using this notebook first. Who is sending something in chat? Okay. So sorry, I have to. We are using this first to download the data set and the rest, and then later we are going to use the other one to do such. So I have to mount my drive again. Sorry. So as we will see with Colab, if the notebook is already is created by the same account, Google account, you don't need to do all this process. So you will see it later. And do I have the audience?
Yes, the audience is around. You're all here.
Okay, so sorry for taking much of your time. So that I am in the right directory. So when we load everything. So here we load matplotlib in line so that we are able to draw. So the first code we see as in the textbook is trying to download this data. So this data will be downloaded into a new folder called data on version page 17. So we download this. So as we see now, the data set is downloading and it's extracting into this. So if you refresh here, you will see a new folder here, and it's called data on version, and you will see here. So it's already downloaded already. So now we can start working on this. So we initiate our class names, and initiating class name, we saw it there. We saw that we have 10 classes, the aeroplane, automobile, and the rest. So here what we are doing is we are taking for the number of classes, we are plotting one figure for each class. So for aeroplane class, we for automobile, for bird, for cat, and the rest. So this code does what it does. It's showing the plot and the rest. So now go back to
do
you want to
I
add something?
Add something. Yes.
Okay.
So in this code, as we can see, it is said from Touch Vision import data sets. So import data set is basically, as he said, a module that allows you a data set that allows you to data, right? But what is we can see we say data set to CPAR 10, right? So Pytorch implemented different kind of off-the-shelf data set that you can download as a function. So CFAR 10, I think, is a custom function that allows you to download only CFAR data set. So there are many other data sets that they use this name. So this CFAR is not like something in Python, but rather it's just like a kind of, I think it's function, right? Is it function code? It's function code. Yeah. So maybe there are some other name of data set, like what are the other names?
Yeah, it's MNSIT, version MSIT,
So if you,
and the rest.
yes, so if you are downloading MNIST, so here you put the .MNIST, right, and to download them. So this is just a custom function. But also, what about if you have your own data set? Like you are not downloading this free-made data set from Pytorch. So in that case, you need to create what is called custom data set. So this one is like predefined data set that you can use for like just experimental teaching and seeing how Pytorch work. That is how you. But if you are now have your own data set, you created your own data set for maybe sentiment analysis. This means that you are not actually using CPAR this way. You need to do what is called custom data set. So this is something that
I have a quick question, please, Doctor. What I want to understand is, with data sets, just like you have explained, so is it particularly done when you're using image processing, that if you're using a data set from, let's say, one of the organizations that have this data sets open, and then you have your own data sets that you have to now differentiate between any data set that is with you and other data sets that are actually free online that you can download at any point in time?
I think your question is not that clear. So if you may clear
what
it,
I want to understand is the difference. He said, like, when you're trying to load your own data set, you have to create a custom data set.
Yes.
But there are situations whereby with, let's say, the Cypher 10, I can maybe download it and keep it with me, not just to do it online. So what difference does it make now?
So with regards to this is, if you have the data set already in a local directory, it will not download it. If that data set that you have locally,
will you use the same name, or will you use the custom?
Yeah, and that's the problem.
I think can you go a little bit?
I think I have the answer.
Here you can see you said download true, right? If you said download false, it means even if you said I think download false, it may not download it to take if you specify in the particular path. I'm not sure, like maybe Falalu, you said you are an answer. And what I'm saying is this custom data set is this. So these are predefined data set that you just download. There are tons of them. If you look at I share a link. Now you download them and do your experiment. Now, if you download them now already, you have them in your local machine. You want to do some kind of, you don't need to re-download them because you already have them, right? You can just provide the path for those. So the main essence of this class, I think, is allow you to create a data set, to download a data set, right? So you can see if you have it, you don't need to download it, right? So, but for the purpose of creating custom class, I shared another one, maybe link. I think in the book they didn't explain maybe another further. Custom data set is to allow you to create your own data set in your own way, But remember also, these data set, they are different if you are loading image data set. So you can see here we say from touch vision input data set. What about if you are using NLP? From where are you going to download those data sets? So we have touch vision, we have touch text, which is basically for doing text stuff like NLP, and you can download some stuff. So the link I think I shared from the Python, you can see in of class. Finally, can you add what you?
No, you have answered the questions. When you install Pytorch and maybe you provide touch vision, you have all the data sets locally. So you just need to maybe use the function to call it. You have answered the questions. When you import the data sets, you have all the data sets already with you. Can you hear me?
Yes, we can.
Yes, we can.
I think
Yeah.
the
So
chief
if
has answered the question.
okay, so if we may continue. So as the Shamsu said, there are many types of data which we've seen in here, and I even run this code to like we have the CFAR, the Celeba, Cityscape, the rest, Coco, Country 2211. So they are all different types of data that you may want to use in your work. So you can go and explore what type of data is held in that data set. So if you run this method retribution, what you see is the type of the data. So where it is. So it's in the data set, it's in the vision data set, and it's in CFAR 10. So these are just basics of the characteristics of the data. So in the data set class, so we said this data set is in the touch utils.data the data set class. So if we look at it here in this figure, so what they are trying to tell us here is there are two methods that you can use to manipulate this data. You can find the length of the data and you can get a particular item in the data. So it's just like list. If you want the first element, you can say 0. If you want the second element and the rest. And you can run the length method to find the length of the data. Let's run this. We all know how to run length to get the length of the data. I know that one. Cool. Let me delete this output. It's too long. So now the length of our CFAR data, as we can see, is just 50,000. So we'll continue. So to get a particular item, as we said in here, you can get the CFAR when returning, when it returns the image and the label of the image. So the labeling is just like the class. So for each class, we know, I think there are this. Yeah, so for 0 is plain, for 1 is automobile, and the rest. So for bed is 2, for cat is 3, for deer is 4, for dog is 5, and the rest. So the label that it will return together with the image when you call, when you index the data set, is you are going to get the image and the label. So the image, the label, and the class name. So the class name, because we've initiated our class, so if you pass in the label, it will give you the class. So in here, if you see, we'll get the description of the image. Is an image file. Its mode is RGB and its size is 32 by 32. And the label is 1. That means it's an automobile. So if we run this code too, we'll see that. So these are all, yeah, these are all preliminary. So, and yeah, image. So we can plot the image because we took only one image, image number 99, and it's a car. Yeah, Dr. Shamsu, do you want to say something?
No, go on, go on.
Yeah, so it's a car, and we've seen that. So now to do data transformation. So why do we transform data? So to transform data, when you want to work on neural network, you know what we need first is to convert any data that we have into tensor. And we have a method that does that. We can do cropping. So all of this come with a module in the third division class called transform. So from this, you can crop your image, you can resize it, you can convert it to tensor, you can convert it into a different format. Let's say your picture is in JPG, you can convert it into PNG and the rest. So
what
among
about
these
if it is a text? What kind of transformation we can do if it is a text?
Oh, text is not on in touch vision, I think, yeah. So, but even if it is a text, you convert it into tensor before you start working. Because what we want to show, like the main thing we want to show in here is you don't work with a text, you work with numbers. And those numbers are the actual representation of that data. So whatever data it is, whether it's a text data. So whether it's a text data or an image data or voice data or any data, you convert it into tensor. So Touch Vision presents a module called transform that have a method called to tensor. So this method will automatically convert your data to tensor. So you can do it in two ways. You can either call touch transform to tensor, and then you pass your image, or when loading the image, because we've said using the data class, where is it? We can do the download is equal to true. So here you can pass the transform as an argument, and then you give it transform dot to tensor. So you can do the conversion directly without loading the actual images, but only the tensor representation of the images, or you can upload the images and then you convert them to tensor. So there are two ways to do that. So here we create an object called to tensor, which is transform dot to tensor, and then we just pass this image into that. And if you print the image dot shape, you will get a tensor representation. And as we've said, we have three representing the color channel, which is RGB, and then the height, and then the weight. So we have the channel, the height, and the weight, which is a tensor. And this is the actual representation of the image. So in this tensor, it contains the data that they represent the image. So now we see our tensor has been turned into this, and So the next one is how, as I explained, when you have, let's say, tensor CFAR10, instead of just CFAR10 is equal to data set the CFAR10, you give the data part, the train equal to true. In here, you see we say download is equal to false because already we have the data. So if to say we don't have the data, we just say download is equal to true, then we pass transform is equal to transform to tensor. So directly it will download it in this part and then convert it into tensor directly without requiring us to follow this other step of doing the conversion. So, but here we set download is equal to false because we have the data already in the local storage. So is it right time we go into the code, or let's continue? Maybe we'll go into the code. So at this, yeah.
My question is, we said train true. What of the validation? Does it mean we don't need the validation data set?
Yeah, we need the validation data. In this case, we don't need, but as you will see towards the end of the chapter, we'll need the validation data when we are going to find the accuracy of the model that we train. So we'll convert that also into tensor, and then because here we are just explaining this to tensor, so it doesn't make sense to convert everything at the same time and then showing, because we are not using the validation set for now. But when you will use it also, you have to, because you've already downloaded.
Validate true.
Yeah, you use the CFAR validation because there is CFAR to do that.
Okay, thank you.
Okay, no problem. So to access the element, you can just access the element of the data set. It will return a tensor rather than the image because we've already transformed it into an image. So there you see when we call tensor, when we call CFAR 99, what it returned is it returned the image, it returned the label, which is 1 in that case. And then if you check the class, you see that the class is it automobile? Let me see. But here for the tensor representation of the data, if you call the data, you will have the image and the label. So, but since we don't do the label, we just use the underscore. So we have the image, and if you print the type of the image, you see that it returns a tensor instead of returning an actual image. And you can find its shape and you can find its type. And the shape is 3 by 32 by 32, as we know what that means. And the type is a floating point number, which is how we,
some of us may not know why do we use underscore here, because if you can add like y in Python so that maybe some people can understand more.
Yes, so if you have a method that returns, because in other programming languages, you can only return one value at a time. Programming languages such as Java, which I know, C++. So, but in Python, you can return multiple values at the same time. You can return multiple variables. So if you call tensor.cfar, as we see in I think we have here that we saw that it returns two values. The first value is the image, and the second value, yes, as you see here, the first value is the image and the second value is the label. So if you call here, it will return this in this arrangement. So the first one is image, the second one is the label. You need two variables to store what it is returning. But here, what we are trying to see is, because the label that it will return is the same label, it's just one. But we've already showed the example here that here it return an image and a label. So in that other instance, we are not, we just want to show the image only. So we are only interested in the image. So if you are not interested in that, you indicate that by underscore. Because if you just say image underscore t is equal to 10, so it will tell you that it returns many value that can be accommodated in the left-hand side. So you have to select which of the variable you want and which you don't want. If you want all of them, you say image underscore t / label is equal to this. So you have created two variables already, the image and the label. But we are not interested in the label, so you just have image.t, underscore, and then cipher. So it will return all of the two, but then you have your variable image t and you can use it. Dr. Shamsu, do you want to add anything else?
Said it all, I mean, so I think this, I'm not sure whether object. So what this
network today is given an issue.
Do you hear me?
Yes, now.
Okay, what I'm saying is like this tensor CPAR10 it actually returns, I think, a tuple, right? It is, I'm not sure. Yeah, I think it returns tuples. So it is tuple here that returns this object. What this tensor CPAR10 returns tuple. So in Python, as you already explained, was like it returns two items. So if you don't want to have the second item, you can just put underscore. So, but there is no issue. You can even put X, but you don't need it. So that is just like in Python, one notion that you just use underscore. But I think what this guy returned is Python tuples object rather than any object. So it is a tuple object that we use this convention to
even lists too. Yeah,
okay,
if the size of the list,
right.
Yeah, if you have, let's say, two items in a list and you give in image, label, so the first one will be stored in the first, the second one will be stored in the second.
Okay, yeah. So yeah, okay, we can, yeah, that's good.
Because that's the Python sometimes is nice. Almost all the time is nice, because if you don't want a variable, you don't need to create it in the memory. So you just
so that is
so
that is one, I think the reason why is like you don't want to your memory, you want to reserve your memory, right? So if you don't want it to return, for example, you have 10 million, you want to return 10 your object return 10 object, and you want to only use one object. So instead for you to return all the 10, you can put image image t. Then if you don't want to return all the remaining 9, you can put, I think, is it star underscore? Is it star underscore? Yeah, star underscore will not return the whole 9 objects. So the image t underscore t will take the first item, and star underscore 9, all the other 9 objects will be discarded, will not be stored in memory. So yeah,
it's
so
the same convention with I think with Prolog.
Okay.
So we call it I don't care. So if you don't care about the second,
yes,
then you put an underscore.
Yeah, so I star underscore. Falalu, you can remember this thing we did in our Python session, right?
Yes, sir.
Yeah. So yeah. So that's one cool thing. So that's why Pytorch is so Pythonic, right? So if you know Python, like this is one cool thing. Yeah, impact from Pytorch. What does that mean? Py comes from Python, and torch comes from because there is existing language called Torch, right? So Pytorch was built on top of Torch, but with Python. So that's why it's called Pytorch. But Pytorch contain many code for other C++, not only Python, for speed and other stuff. So that's why Pytorch is beautiful in Python way. Yeah, thank you.
Okay, so thank you for that. So whereas in our original image, you are going to get 0 to 255, which is 8-bit per channel, meaning 0 to 255 indicates the indicates the value of your red, green, or the rest. If you convert it to tensor, it's going to convert into a 32-bit floating point per channel. So it scale the value down from 0 to 1. So, and you will see the in there. So here you can print your image.minimum and image.maximum. So you'll see that it's from 0 to 1. So is the range that you will get. So instead of from 0 to 255 in a normal image. So to verify that we are getting the same output, so you see, even though you've converted into Python, you can still plot it. In there, we have, we could plot it as the image file. In here, we have we will see here, let's verify that we are getting this. So we change, instead of using channel height and width, we change it to height, width, and channel. And we saw it in previous chapters, that when you load a data set or you load an image, I think is it chapter 3, how you represent data. So sometimes you need to permit it to give it in this structure. So here is 32 by 32 by 3, but what you want actually is 3 by 32 by 32. So you have to permit it. So to show it here, you permit image.t and then you plot it using the matplotlib library, and you see that we have the same image as the previous image. So nothing is distorted. So although you've converted the data from the image PIL image type to the tensor type. So normalization of data. So we all saw normalization of data. Do we need to go into why we do normalization of data? I think when Dr. Shamsu was, explaining chapter, is it chapter 4 or 5, Dr. Shamsu? I think you made mention of the why we need to normalize data. Sometimes the data set is in a range that is very big. So you have to scale it down either by multiplying it by either 0.1 or any scale that randomly make the data to be in a format that the model will learn more easily and faster. So in here too, we do normalize image data. So doing the normalization, I think we saw normalizing, subtracting mean, and then dividing by standard deviation, so that each channel have 0 mean and unitary standard deviation. So it, so yeah, the set, we mentioned it in chapter 4, and going through chapter 5, it was mentioned too. So here we're in chapter 7. Dr. Shamsu, do you need to remind us on, or should we just skip?
You can skip. We just assume we.
Yes, so it's just similar.
What about here?
Yeah.
No, there is some issue here, like touch stack. Maybe we can explain. I don't know if.
No, what I mean is we've normalized the data. Now, yeah, we can. So touch the stack, what it does is it, we all know stack. So it's just stack of tensors. So we put in tensors in the form of stack data format, and then using that, we can calculate its mean, we can calculate its standard deviation.
But why do we need to stack them? What is the idea of stacking them? Calculating.
So here, if we see what we have originally is a vector of size 3 by 32 by 32, meaning we have a tensor of only one image. So to find the mean of all of the images, you need to get all of your images in one tensor. So by getting all of them, you can find the mean and the standard deviation of all of your images, not only one image. So that's what I understand with this. Is there any additional thing? So we normalize across all of the images instead of just normalizing only one image. So, and we find the mean, we find the standard deviation, and then we do the normalization. So normalization is just adding, subtracting mean and dividing it by standard deviation, but transforms, yeah, which is a module in touch vision, allows us to give pass in the normalized data for it to do the automatic normalization. Yes, you want to say something?
Can you go a little bit up, please?
Yeah.
Yeah. Okay, cool. So right. So here where we say total stack, you can see here we have like a list comprehension, right? For image T, and this is the level, right? We don't care about the level. In the this tensor returns the image, right? Now when it returns the image, then we will have a single image. Then this stack is the one that stacked them into 3, the dimension 3. So I don't know if I understand this correctly. So here we have the list comprehension first as the first argument of stack. Then we have dim of 3. Now this list comprehension says for image T and the level, which we don't care about the level, in the tensor, and the tensor just have 2 things, right? The image T and the level returns the image. And now when it means this list will return all the images, right? In the form of these 3, 32, as you said. So then we provide the dim. So the stack contain arguments, I think, right? The stack contain 2 things: the your tensors, then
Your
the
list of tensors,
then the dimension, correct?
Yes.
So here taking this list of tensors and putting them in the dimension 3. Is that correct, or you want to add something? If I understand it.
Yeah. So we all know stack. It's just like Pringles. We all know Pringles. They keep chicken one. So there is on top of that. There is on top of that. And if you want to take them, we all know push, pull, pop, and all of those things in data
I know.
structure.
Yeah. So
So what we have here is we are stacking all of the data set into one tensor, so that it will enable us to get the mean.
Yeah. Okay. What about this one? Image.view.min.dim one. What is it doing?
So image.view, we all know view, what it does is it changes the shape of the tensor without changing the actual tensor in the memory. So what it allows us to do is it changes it. If you see the note at the side, so they call that view keeps the 3 channels and match the remaining dimension. So already this is just the size of the number of images, but what you actually want for each image is this 3 dimensions. So it keeps the channel and then it multiplies the rest. So you have 32 by 32, which is in here. So, and if you transform it into this type of vector, the mean is taken all over this 1024 elements in each channel. So in the red channel, the green channel, and the blue channel, you all have the mean along that channel. So if you see our output here is RGB, which is in the R is 0.4915, the G is 0.4823, and then the B, which is the blue, is this. So this is, we are normalizing the colors, which we are normalizing the colors, and we'll see after this normalization how the color changes in the actual images.
So here dimension min dimension 1. What's this dimension 1 is saying now?
Yeah, so you have 1-dimensional data set instead of the 3 dimension that you have with each the dimensions specify that you are finding the mean along the rows, not the columns. I think so if you are finding you can find mean along some certain direction. You can find mean along either the mean of all columns or the mean of all rows. So I think stating the mean dimension 1 is it find the dimension along the row, while if you say dimension 0, it find the mean along the column. So because you have like a matrix of data that is 3 by 1024.
So this mean is in place, right? Because I can see we have not assigned anything here to, is it doing this computation in place? Is that correct?
I didn't get your question.
Okay, what I'm saying is that, here we have the image IMGS line 15. Yes. Now here we are saying image IMGS that view 3 minus 1 that mean dimension.
Yes.
We are not assigning this thing to anything, right? So what I'm saying is doing the operation in place. Is that correct?
During the operation what?
So do you know in place?
Yes.
Do you know in place operation?
Yes, an operation that changes the value of the original variable, not you need to store the result after on a different distance. Yeah.
So what I'm saying here is that the mean operation here is in place operation because we are not assigning the result to anything. Is that correct?
Yes.
Okay. Cool. Sorry, character so he started getting bad. Sorry.
Yeah, sorry. Me too. I did it in the morning. So
continue.
yeah, so with these numbers in our hand, we can initialize the normalization transform. So you just send in you have transform to normalize this. It will bring the output that it will take the first argument, which is a tuple of dimension 3, and the second one as the standard deviation. So if you initialize this transform to normalize this, it will normalize, taking the first one as mean and second as standard deviation. So if we see the same thing we are doing here, we are transform CFAR 10 is equal to dataset.cfar. So you see, you can do all of these things when creating the dataset, or you can do it after creating the dataset and then you transform everything. So here, transform.cfar 10 is dataset.cfar 10. You give the data part, you tell it that you want only the train data, not the validation data, and download is false, meaning you are not downloading. And then you pass this. Transform is transport.compose. Why compose? Because we are passing multiple arguments. The first one is you first want it to be converted into tensor, and then after converting into tensor, you want it to normalize using this. Yeah, using this. The first one is the mean, and the second one is the standard deviation. So it normalizes. So at this point, plotting an image from the data set will provide us a faithful representation of the actual image. So you see the image will be distorted. You see, before here is some kind of like plant tree, and you can see it's some of the colors here, but it's broaden or make the actual image that we want in the data set much more pronounced, and all of the other site information it gets lost.
Yes, in the tambaya.
Yes, I hope not.
So when I transforms that compose.
Yes.
What do you say? Like because we have many.
So yeah, if you are passing only to tensor, you don't need to say dot compose, because the dot compose means you are passing multiple transformation tasks, and make sure you give the task like sequentially. So you want the first one to be done first, and then the second one to be done second, and the rest. So if you have any order that you want it to come after normalization, you can find you can put it there. So let's say, or maybe the first one, let's say transform.crop. First, you want to crop the picture. Then let's say transform.resize. You want to make it in a normal size. Then transform.to-tensor. Then after doing all of that cropping and resizing, you want to convert it to tensor, and then you want to normalize it. So you see what you mean here.
So here, which one do we do first? Is this normalize we do first, or to tensor we do first? Which one?
No, we have to convert it to tensor, because we are normalizing only on the converted tensor representation of the data. Yeah.
So I'm thinking this one is we have what we call something like composite functions in math and also in Python. So we know like we can have like f of x, g of, you remember in mathematics composite functions where you have like f of g of f. In that composite function, which one do you do first? Is it the inner one you do first, then the outer one? Do you understand what I'm trying to say?
You do the inner one, then you do the outer one.
Exactly. So this one is not that way.
Is it a question?
Yeah.
With regards to this, so sometimes you may not read deeply to get so I have not read that, so I cannot give you in that perspective, but to my own perspective here, it makes more sense, or it's only possible to normalize a data when you have converted it into tensor. And what do you mean by converting it into tensor? You have to convert it into a number. So let's say you have a PIL image and a PNG image. So how can you normalize?
Yeah, I know you need
Yeah.
to do that, but
Yeah,
my
so
thinking, I'm just trying to
a kind of
put
more
it
explanation
in
yes.
perspective of mathematics stuff, like trying to see like what is because this is, I think the idea is coming from mathematic composite stuff like that, composite, which is also
Yes.
that's in Python sub. Let's go on. Just like want to get more clear.
Yeah. So we've drawn it, and you see this is what it. So now the problem that I described at the beginning of this is that Jane is our friend at the bed watching club. We all have a friend, Jane, that is a friend at this club. So what she does is she set up some cameras, and this camera will try to be looking at birds and aeroplanes and anything that goes into this place. If it is a bird, it should be published in her blog. If it is not a bird, it should be discarded. So that's what she wants to do, because birds and aeroplanes, as we see in here, sometimes they can look the same if they are in the sky. So it's just something like just plus or T or whatever. So, but what she has been doing is she has been, the camera used to notify her of everything. Whenever an object enters, the camera will shoot the picture and then it will transfer it to her server. But then she will come manually and try to see which are aeroplanes and which are birds. She delete all the aeroplanes and she keep all the birds in her blog. But then this is a very cumbersome task, because as they said in here, there are more number of planes that fly in that area than birds. So she have to delete many things manually. So instead of doing this, what she wants is, she wants an AI to throw the planes away automatically without her interfering. So now this is the model that we are going to build. So to build the model, as we know, in the CFAR 10 dataset, it have 10 classes, but here we are only interested in 2 classes, the bird class and the aeroplane class. So, and all of the other classes, we are discarding them. So in here, you see what we have here is the label map. We are selecting 0 and we are giving it 0 and 2. 2 represent bird. We are changing its value to 1. So that in our data set, we only have the labels as 0 and 1. For 0 means aeroplane and 1 means bird, instead of saying 0 and 2 as in the original data set. So we are changing the label. So class name now are only bird, and instead of the 10 classes. So now CFAR 2, because we said CFAR 100 contain 100 classes, it was created CFAR 10 with 10 classes. So now we are creating a custom data set called CFAR 2. But it's a subset of the original data set. So what you are doing here is you are returning as a tuple the image and then the label and the label map. So if the label is 2, it will be represented as 1. If the label is 0, it will retain its value 0. So 0 for aeroplane and bird for 2. So for image and label in CFAR 10 data set, if label is in 0, 2, that means if label is either an aeroplane or a bird, we are returning that instance of data set, which is an image and a label. And then we are formatting this. We are leaving the image as it is, but we are changing the label to become either 0 or 1, which means aeroplane or bird. So also we are creating our CFAR 2 validation from our validation data set. In here, we are building from the training data set. Here, we are doing the same thing, but on the validation data set. So now also, since this is a subset of the object, it has also those functions of length and get item. So you can get your length and you can get a specific item. Should we go and run all of the codes all to this place before continuing, or can we continue?
Yeah, you can continue, I think.
Okay. So a fully connected model. So we all know what a fully connected model is. It's a model that from one layer to another layer, all of the nodes, all of the neurons in that layer are connected to the layer in the, in the subsequent layer. So each preceding node is connected to all of the nodes in the subsequent layer. So we learned how to build a neural network in chapter 5, which Dr. Ibrahim did a very nice job. So we know that it's a tensor of features in and features out. So you get features in, you get features out. You first get your data, convert it into tensor, pass it into your neural network, it does some computation on it, and then it produces a result. And all of those are just tensors. You get tensors, you give tensors, you get tensors. So after all, an image is just a set of numbers laid out in spatial configuration. That is, we don't know how to handle spatial configuration just yet. But in theory, if we just take images, pixel, and straighten them, why we are not taking this is because we will see it in the next chapter, how to use convolution to read images. It gives us more sense, meaning that one pixel can be associated to its neighboring pixel. So 0 can be associated to 1, it can be associated to 4, it can be associated to 5. So also 6 can be associated to all of these surrounding pictures. But in here, we are not there yet. We will see that in our next chapter. So how do we do this? We flatten it out. Meaning we have 0 to 1 to 3, 4, 5, 6, 7, 8, and 9, 10, and the rest. So let's try that. How many features per sample? We multiply 32 by 32 by 3, meaning you have, for your input, you have 3072 by flattening it out. Features per sample. Starting from the model we built in chapter 5, a new model can be a linear model with 3072 input features, some number of hidden features, and then your output feature. So in here we define touch.nn as we see in the last chapter. This is neural network. So your number of output, because what we are doing is we are classifying only 2 types of objects. So it's either aeroplane or bird. So the number of output depends on the number of classes that you have, target classes. So you define your model as an NN sequential model. You pass in the linear with the input features and the hidden layer size. You give your activation function here. We are using Tanch, and we pass in the output. And the output is the hidden layer and the output layer, which is 2, size 2. So you are given 3072. You are expecting your hidden layer to do all sorts of computations. And at the end, you want your output to either be 0 or 1, or any number that is closer to 0 or closer to 1. But we'll also see that using 0 and 1, because it's a classification problem, and we saw in chapter, is it 3 or 4? Chapter 4, that classification task is better done using a one-hot encoding. So you either have 1 and 0 for aeroplane, or 0 and 1 for this thing, so that you can put them in form of probability and the rest. So we are going to see that too. So the output of a classifier. So the network produced the predicted temperature in chapter 6, and we saw temperature, and we use the MSE loss, mean square error loss, for our loss function or cost function. And we have, yes,
okay. Can you go back a little bit?
Okay. Yeah, we flatten out our picture from 3 by 32 by 32 to a single sequential
okay.
input.
Okay,
So we
that's
just
another
multiply
3 by 32 by 33, right?
Yes.
Okay. Right, I see it. Shine by the 3072. Okay, cool.
Yeah.
Can you go down a little bit as well? So 1 and 3, 3, 5, 1, 2. Is it fixed? I can see like they say that arbitrarily pick it. So it is you
Yes.
that you are designing your neural network that you
Yes.
determine the number of hidden layers you want, correct?
Yes.
Okay. So
And most of these things are not done like just by head or sometimes by calculation. Sometimes it might surprise you that you have to actually do the experiment to know which of your parameters are very good.
so hidden layer, number of hidden layer is also parameter tuning. Is that correct what you are saying?
Yes.
Right. Okay. Cool. Now got it.
So, and what you are, I don't know, but let me give a kind of a statement here, which I might be right based on common sense, or I might be wrong based on what I have not read. ideally your hidden layer should not be at the same size or even more than your input layer, because you are reducing up to the size 2. So from the first instance you are reducing to 5 by 512. Then the second you are who wrote something here?
Sorry, doctor, I think it's me. The phone was in my pocket.
Oh, sorry.
The phone was in my pocket, so the screen might do. Sorry about that.
Okay, so let me clean it. Yeah, so if we may continue. So please go and learn, read. I don't think it's too much reading. How you select your input and how you select your hidden layer. But I think it should be that if you have 3072 as input, your hidden layer should be less, and then less up to your classification, your output. So the output here we saw in the previous chapter is just because it's a regression problem. You are just trying to predict temperature, so it's just one output. But here, since it's a classification, you want to give a particular output when it is bad. You want to give a particular output when it is what's it called? When it is an aeroplane. So, and as we said, as a reminder in chapter 4, we have to represent a categorical variable. The set is better if we use one hot encoding. So for each of you have this 1,0 for aeroplane and 0,1 for bed. If you like, you can say 0,1 for aeroplane. So it's not like a kind of fixed something. So this will work if we have 10 classes as in the full CFAT data set. You just have the input, the output vector of 10. So you have 0, let's say 1 and then 9 zeros for aeroplane, and 0, 1 and then 8 zeros for this and the rest. So just one what encoded is. So in the ideal case, the network will produce a tensor of this for an aeroplane and a tensor of this for a bed. But practically speaking, since our classifier we know is not perfect, it cannot deterministically like just see something and just say 100% this is aeroplane, 100% this is bed. It's not even, it doesn't even make sense. So most at times it will try to maximize or try to approach that value. So you might get, let's say 0.8, and you know, yeah, that is an 0.8 comma, let's say 0.2. So you say that is an aeroplane because the first one is bigger than the second one. So getting 1,0 all the time is not possible. Although if you, based on your output, you might say, yeah, let me see if the index 1 is bigger than index 2, print tensor.1,0, so that you see you just manually do that to give you 1,0. But if you are basing it on the output of a model, you basically get this. So the key realization in this case is that we can interpret our output as probability. That means the first entry is the probability of airplane, the second entry is probability of bed. So if you see when you add the sum of probability, you get 1. So 100% probability means 1, while 0 chance of something occurring is just 0. So if you add it, you have 1. So casting this problem in terms of probability imposes extra constraint on the output. Each element must be in the 0 and 1 range. That is a probability outcome cannot be less than 0 and cannot be greater than 1. And we know in our neural network we can have that. Also, the sum must add to 1. That is probability. The sum of something happening and sum of something not happening, if you add them together, you get 1. So to do this, we use the softmax. And softmax, what it does is it gets all of your output and convert it into a range. And the range is 0 and 1 in such a way that if you add all of the output of a softmax function, you get 1 as the value. Am I making sense?
Yes.
Okay. So softmax, this is how you implement it. Let's see the figure first before the formula. So softmax, you divide the exponential of your output, divide by the exponential of all of the other output, including your output. So if you have for aeroplane for bed, you find the exponential of output for aeroplane, exponential of output for bed. So you divide exponential of output for aeroplane all over exponential of output for aeroplane plus exponential of output for bed. So in there, you get the value for aeroplane. So also to do for bed, you divide the exponential output for bed, divide by exponential output for aeroplane, exponential output for this thing, and then you get for that. So at the end, if you, the range is between 0 and 1, and their sum is equal to 1 all the time. So, and this is how we put it here, defining it. Softmax is you are returning touch dot exponential of x. So in touch we have exponential, divide by touch dot exponential of x dot sum, meaning you are summing all of the exponentials, and then you are dividing by that. And I don't know why. Oh, okay, it's a touch. Yeah. So it's a multidimensional. So if you have x is equal to touch dot tensor 1, 2, and 3, if you find it softmax, you have 0.09 and the rest. And if you add all up this, if you add up all this, you are getting 1. I think they did it here. Yeah, if you do the sum of it, you are getting 1. So your probability will also always amount to 1, and the output you will get in the range of 0 to 1. So, and if you get, let's say, after getting the softmax, you get 0.4 and then 0.6. So you know that since 0.6 is bigger, so that is likely to be a bed. 60% chance that that is a bed than an aeroplane. So softmax is monofunction. That so it's just explanation for that. Wallahi kokari a ma ban yi ba. Wai in gama wannan tukunna zan je sha komai da komai. Don't worry. Yeah. So we have this. So as we see in here, Malan Shams, that dimension is equal to 1. I think this is where I saw it most. Yeah. So, and if you have a tensor, multidimensional tensor of 2,3, so you have 2 rows, 3 columns. So if you give dimension as 1, it means it is taking the softmax at each individual row instead of individual columns. So if you give dimension is equal to 0, it means it will take softmax of this column, and this column, and it will return this. But since a 1, 2, 3 represent the RGB of one image, so it's just taking the softmax of 1 of this, yeah, along to the row. So this 1, 2, 3 will be like the one-hot encoding of a particular class. And if you take the softmax, you see if you add all of this, you get 1. If you add all of this, you get 1. If you add the rest, you get 1. So at each instance of your data set, you will get a particular class. And this class will determine that this is the most likely class to occur. And this is also the most likely class to occur with a chance of 66.5%. So now if we come back to our model, if we remember, we define a sequential model of sequential neural network of linear input and linear output. So we have the 3072 as our input and 512 as our hidden. We have our activation function, the tanh. We have our output with the hidden layer and the output. Then we introduce our softmax so that this output layer will be, how do we call it? Is it normalized, or how do we call it?
Which one? The
softmax is, I think it's normalized in between the range of 0 and 1.
Yeah,
the actual what? Yeah, squashing. So it's squash it between this range.
Yeah. So also I want to add, like as you can see, the first and the linear, we have 307. We have the output, the hidden layer 512. So the output here 512 must be the input to the next linear, right? Is that correct?
Yes.
Okay.
So yeah, and that's why you have the same dimension in here. So if it will output it to this hidden layer, which it will serve as an input to the output layer, so that the output layer will output only 2, but it receives as input 512 because the output of this, and that's why we say it's fully connected layer. So the output of this 3074 will be the same input of the linear layer. So does this additional information make sense, Malan Shamsu? Dr. Ibrahim?
Me kace fully connected ko me kace ne?
Yes, we say fully connected layer, that the output of each neural network will be imputed to each of the next layer.
Yes.
Yeah,
Yeah,
so
yeah.
since you have 512 here, you are imputing the same 512 to the next layer. So if you have another layer here, what will then be the input? Question.
Hello? Question kake?
Yes.
Idan ba ta ƙarshe ba ce, in ta ƙarshe
idan ba ta ƙarshe ba ce, idan akwai wata layer me input
will be 2.
Yawwa, saboda is the output, because we are taking it fully connected there. Yeah. So thank you.
Wai yau ni kadai nake ci tambaya ne a class din mene ne?
Na tambaye Dr. Ibrahim ya bani ansa, kuma akwai da sometimes you know how to make some points more clearer. That's when you are our teacher, so sometimes that's why.
Ina ji ni ne ban buga ni ba saboda ni kadai nake ci tambaya da ba wanda yake tambaya ne.
Ai ina ga kowa ya karanta ne, ko kuma kowa baya ganewa ne. Ai an ce is either of the two. It's either you are all understanding or you are all not understanding. Or maybe you leave all the question until after we finish.
Okay, so let's go.
Which is much more difficult coming back to.
Yeah, okay, let's go.
Yeah. So here, if you see our image this in the CIFAR 2, we have plot.image show permit this and that, and we have this. So this is a random bed from the CIFAR 10 data set after normalizing it. So you see, this is a bed. Hoto ne na kamar me take da suna ne, dawisu ne ina ga ko. So before normalization, it is more clear. After normalization, you see how it becomes. Alhamdulillah. So now what we do here is we can process what I'm sorry, where we are we? Yes. So in order to call the model, we need to make the input to have the right dimension. So we recall that our model expressed 3072 images as input, with the neural and that the neural network work with data organized into batches along the 0 dimension. So we need to transform our 3 by 32 by 32 image into 1-dimensional tensor, which is 1,3072 instead of the 3 by 32 by 32. So in here, what we do is we use the view -1, and this will transform the data into 3072, and then on squeeze, meaning it will add a column at index 0. So at the end, you will have 1,3072, and you will put it as your input instead of 3 by 32 by 32. So this is the image batch, and we are considering all of this 3072 as one batch.
Ban ji abin da kace ba. So why do we need to kace kafin mu ba model din mu mai da data mu ta zama 1 by 3072? Why do we need that kace?
Yes, because we are using a linear model, and the linear model expects all of the data set to be in to not be in this format of 3 by or the RGB, which is a channel by height by weight. It just needs all of the features, because our data we know is contagious in cells and rows, but the linear model requires all of the data to just be in 1 dimension. So you are passing 3072 instead of you are passing a tensor of 3 by 32 by 32. So you are flattening it out, as the language they put in here. So by using this view -1, it means you are flattening 32 3 by 32 by 32. So if you are flattening it in kamar inda muka duba wajen min wajen lokacin normalization, we can pass 3, -1, meaning it is keeping this 3 and it is multiplying only these 2. But since we are not keeping any of this dimension, we are just using -1. So it will just multiply 3 by 32 by 32. And at the end, we are not multiplying our tensor, but we are just multiplying the shape, so that all of the data will just be in a single column instead of 3 by 32 by 32, as we see how to represent an image in a tensor. So now our output is equal to model. So we are plotting this image. We are is it plotting? Should we say? Yeah, we are fitting this batch image into our model, fitting, yes. So output is equal to model, and we've already defined our model as a sequential model with linear input, an activation function of Tanch, and a linear output and a softmax layer to squash the output. So at the end, after fitting this image, you will see we'll have a tensor of 0.4784 and 0.5216. So this is the what do we call it? This is the prediction that your image is 47.8% likely to be an 1 and 0. 1 and 0, I think, is aeroplane, Neko. Yeah, to be an aeroplane, and 0.5216 to be a bed. So since the second one is bigger, we have that this model is a bed, but the performance is not much different. So usually coming in the Akayana is just by chance. When is it it may not be correct. So here we get the probabilities. Well, we know we shouldn't get too excited because the weight and bias of our linear layers have not been trained at all. So by training, doing for forward passing, calculating the loss, doing back propagation, running another epoch, and the rest. So we didn't do all of that. So we just fit the model, and this is what it gives us. So in the next subsequent ones, we will see training the model and
yeah. So here go forward pass. Okay, go forward pass.
It's just one forward pass, and that's it.
Yeah. So
so an actual training, ainihin training is just the back propagation. Ainihin training, trying to adjust your weight and the rest. So forward pass is just, I give you, let me see how you can do. Then you do it. Then I see how off are you from the actual ground truth. Then I try to train you to say, yeah, this is what you will change, this is what you will change. And at the end, the forward pass, how can you do now? So the actual training is in the calculation of the loss and doing the back propagation. And we've not done any of that. Yes, the to...
Yes, continue. Yes.
Oh, can I continue?
Yes.
Okay. So a loss for classifying. So in the previous Abubuwa, we said we use the mean square error to do our loss. So in here too, they say we can still use mean square error to find our output probabilities to converge to either 0, 1 and 1, 0. However, thinking about it, we are not really interested in reproducing these values. Exactly. Kawai so muke mi ta rage ɗaya, mi ta ƙara ɗaya. So it's just, she said likelihood. So we'll come to that. So looking back at our Axmark operation, we try to extract the index of the predicted class. What we are really interested in is that the first probability is higher than the second. Koma ya faru inde the first probability is higher than the second, ko kuma second is higher than the first. Zam iya fitin din shi mu ce wannan aeroplane ne ko wannan bed ne. So in other words, we want to penalize Mills calculation rather than painstakingly penalizing everything that doesn't look exactly like 0 and 1. So we are trying to reach as much as we can. We are trying to reach 1 and go away from 0. We are not trying to reach 0 and reach 1. So we are trying to reach only 1. So then let's say we have 10 classes. We are trying to reach only 1 class, and all of the 9 classes, we are trying to reduce them to be reaching. So when the likelihood, so we need to maximize in this case, what we need to maximize is the probability associated with the correct class, where out is the output of the softmax and class index is a vector containing 0 for airplane and 1 for each sample. So the quantity that is the probability associated with the correct class is referred to as likelihood. So the likelihood of our model's parameters given is specific data. So in other words, we want a loss function that is very high when the likelihood is low, so that the alternatives have a higher probability. Conversely, the loss should be very low when the likelihood is high than the other alternatives. So we are really fixated on driving the probability up to 1 and further from all other alternatives. Call 1, 1, 1 in the real class that we want. So there's a log function that is called the negative log likelihood, NLL. NLL expression is the minus sum of the logarithm of the output given this data, where C is the correct class sample at sample I. So in this case, if we see here, the loss is coming down as we approach 1. So we are targeting only a single likelihood. And as we are reaching that likelihood, our loss is reducing, not taking into consideration all other options or all other choices. So here you see, if instead of passing the softmax, we can just pass the log softmax. And what this means is, they said there is a good reason behind input convention. Taking logarithm of a probability is tricky when the probability gets close to 0. So the workaround is to use the log of softmax instead of using directly softmax, which takes care of calculation numerically. So also we said we are trying to leave all of the others. So what's dollar that's it approaching 0. One kuma guda ɗaya a ciki will just be approaching 1. So when as they approach 0, you can find wani ma ya zama 0 completely, saboda wataƙila ba shi da wani chance na zama wannan. So, and the log softmax is better suited for this kind of problem rather than using only NN softmax.
Yeah. So I want to add something like we should not forget in the previous chapter we talked about what is called activation functions, right? So this is one of the I think challenges issues. So each activation functions, they have their issue and stuff like that. This is what one of the issues with softmax. So that is why it's replaced with the log softmax. And we should all know that here where we have NNN.tench functions, activation functions, and we have log softmax. So we have activation functions at hidden layers, and we have activation functions at the output layer. So activation functions at hidden layers and at the output layer, they differ. So not all activation function that you use at hidden layer, so for example, now TenH is activation function, log softmax is activation function. This means that you cannot use tench as the last output and log of softmax at the hidden layer activation function. I think we didn't discuss this in the previous session, that all these activation functions, they are categorized into maybe in general sense 2 ways. Those that are used at hidden layers and those that are used at the output layer. For example, softmax, cross entropy, stuff like that, they are used at the output layer. I don't know if that's anything on this.
So do we have anyone that want to add anything here? So if there is none, I hope we are all together. So yeah, the next one is after defining your model, which is just similar to what we did before, just changing the softmax to log softmax. We define our loss, and our loss, instead of the MSE loss, we said we are using only the negative log likelihood loss, which is the NNL loss. Sorry. So the loss takes the output of the log softmax, which is the prediction, and it compares it with the ground truth, and then calculates the loss. So here we have our image. We've fitted our image after unsqueezing it and after flattening it out into 3072 to match our input and unsqueezing it. So we pass the output, because the output is the prediction here. We pass the output with the label that we have in our data set, and the label is we touch the tensor label. So we convert the label into tensor and we compare it with the output that was produced. So, and the loss that we obtain here is 0.65 using the NLL loss backward. So yeah. So ending our investigation of losses, we can look at how cross entropy loss improves over mean square error. So, and we'll see cross entropy is just extension of or adding this NLL loss and something else. We'll see it, the log softmax. So this diagram, I tried to know what it means, but I couldn't. Sometimes. So training our classifier now. So this is now our actual training that we do. So first, we define the model with all of its parameters. We define our learning rate. It's just 1 epsilon minus 2. We give our optimizer, which we are using the stochastic gradient descent. We are passing the model and its parameters, and we are giving it the learning rate. So we now define our function as NLL loss. We state that we are doing this over 100 epochs. So for each epoch, in this range of epoch, meaning from 0 to 99. So for image and label in CIFAR2, so we are taking each image. So for each batch, we are taking only one image, and we are training the model on an instance of one image, and we'll see this in the data loader when we come, how to give it in batches. So here for image and label in CIFAR2, our output is fitting the model, and then we calculate the loss function, and then we reset the gradient of the optimizer. We calculate the back propagation, the loss dot backward. Sorry, yeah, we calculate the loss, and then using this optimizer the step, we do the back propagation, and then we come to the next image. So that means for the images, we have 50,000 images. Oh no, not 50,000 images, because we've selected only a subset of the images for these two class. So for that number of images, then times 100. Meaning for 100 epochs. So we train, meaning we go through the data set for the first epoch, then we go to the data set for the second epoch, and the rest. So we find our epoch, the loss, and yeah, we print this out. So for this, with every sample in the data set, we evaluate the model. That means we do forward pass, we compute our loss, and then the accumulated gradient of the loss using backward, and then we update the model with the accumulated gradient descent. For the second option that we have, with every sample in the data set, we evaluate the model, compute the loss, compute the gradient descent of the loss, and then update the model with that gradient. So if you see, because we said we are training on one single data set at each iteration, then before going to the next epoch, so we can accumulate all of the gradients on the whole data set, and then update the model using the accumulated gradient, or we can update the model with that same gradient of that same picture. So for each epoch, for each image, we will be doing back propagation for each image that we train. So the next one is we can split our data set in mini batches. For every mini batch, that means for, let's say we have 20,000 sentences, we can split it into mini batch. So for every mini batch, with every sample in the mini batch, we evaluate our model, we compute our loss, then we do backward propagation on the accumulated gradient, and then we update the model with the accumulated gradient. So here we are finding the gradient, we're accumulating it, and then we do optimizer.step. So there are three options that we have here. So, but to implement the next option, the third option here, we have to split our data set into mini batch. So this is called mini batch training. So most of deep learning tasks you see, you train in mini batches because it's faster and the rest. So it also depends on the strength of your GPU, the size of your RAM, and the rest. Yeah. It's like somebody wants to ask a question.
Yes. In this using mini batch, doctor, yes. I think it is that where some, if I read some papers, it's like they are using what is called the experience replay. Is it called experience replay?
I've never even hear it, but I think I will have to read it.
Yeah, in the experience is like there.
Yes.
They split it into batches. Mini batch.
Yes. Okay.
Well, I can talk to session, so maybe you can add something. I'm asking, I think maybe in the data experience replay method, they split it into mini batches. So I don't know if we have, yeah, I'm asking question.
Experience replay
Experience replay here.
optimization.
I think it's a memory like that.
Okay, experience replay optimization.
Experience replay. Oh.
Or is it memory or optimization?
It's like they call it experience replay. It's a memory. They call it a memory because they store the mini batches, I think, inside the, I don't know, I read it, but that is why I want to ask question whether we are to use it.
Yeah, I've not read it. I don't know what it is.
Okay.
But I think we may have explanation here. This means instead of running Q learning on the action phase, we store the agent experience and the rest. This needs some in-depth reading. I maybe in our next class, if let us all read. So maybe we'll discuss the idea there.
Okay.
Yes, I think it will be better. Huh?
Is an optimization, is a new optimization technique?
Okay, thank you.
Okay.
I said, is it a new optimization technique?
Yeah, just put in experience replay because they said experience replay, there is a memory, there is also optimization technique and the rest. So, but I think the foundation idea is just the experience replay. So yes, they implement it in the memory, in the optimization, and maybe there are other distance. But here I'm seeing that most of it has been implemented in reinforcement learning and the rest. But if we read it further, I think we'll understand more, and then maybe we'll discuss the idea in our next week.
How it can be implemented.
Yes, and what it means and how it can be implemented, and maybe its advantages over other methods that can be compared with it.
Okay, thank you.
Yeah. So please, this is much more of this thing. We can go and read it. So here, data loader. So in our training code, we choose mini batches of size 1 by picking one item at a time from the data set. As we see there, we say for each element and label in the CFAR2 data set, we run all of our training. So touch util it shuffles the data and organizes the data in mini batches. And the module is called data loader. So the job of a data loader is to sample mini batch from a data set. It gives us the flexibility to choose from different sampling strategies. So we all know the usefulness of sampling in deep learning, machine learning, and the rest. So to remove bias, to train on the data set that is truly random, so that your model will be able to generalize more without any bias of you picking the data set that you want by yourself. So this data loader, it shuffles the data set before giving you the next batch. So if you have your data set with this length and get item, which are the two major methods we have, as we said. So using the data loader, you specify batch size and you specify whether you need shuffling. If you don't need shuffling, as we'll see, if we come to do, if we come to look at the validation data, that we don't need shuffling, we just need the batching to be done. But in the training specifically, you want your data to be shuffled so that at each batch that you are given, you need a thoroughly shuffled data so that the model will learn objectively. So let's see how it's done. At a minimum, the data loader constructor takes the data set object as an input, along with the batch size and the shuffle boolean, indicates whether you need shuffling or not. So you give the trail loader, it's called touch.util.data loader. You can import all of this touch.util.data loader as, let's say, DL, and then you just use DL instead of doing all of this long thing. So the CFAR data set is the data set that you've already loaded. The batch size that you want to be working on 64 items for each batch, and you want it to be shuffled whenever the next batch is generated. So the data loader can be iterated over, so we can use it directly from the inner loop. So by rewriting our previous code, so you've already import everything. You specify your data loader. So you define your model, you give the learning rate, the optimizer, and you define your loss function, and you specify the number of epochs you need for the training. So instead of saying for epoch in range epoch, which is 100, for image, comma, label in CIFAR 10. So instead of taking the data, you give in the data loader. So at each of this iteration, it gives you a randomized sample of 64 images, so that you work on all of these 64 images rather than working on only one. So you can find your batch size. Already we know our batch size is 54, but finding it using image.shape, you can find the batch size as the first entry in it. So it's 64, comma, the other dimension. So you find your output, because here is not a single output, there are multiple outputs, because you are processing 64 at each time. So you fit model on images.view.batch size, comma, -1. So it's 64, comma, -1. So it means you have 64, comma, you flatten all of the others. So if they are 64, comma, 3, comma, 32, comma, 32, so it will be 64, comma, 3 times 32 times 32, which is 64, comma. Because before there we saw, we just used view -1 dot on squeeze. And that on squeeze, it means it's just 1, comma, 3074, meaning we are using a batch size of 1 at each. But in here, we are using a batch size of 64, then comma 3072, which is the number of inputs that you are given. So you calculate your loss, you zero your gradient, and then you calculate your loss and do back propagation. So at each of this, you see your training time will reduce, but this depends on the size of your RAM. So if your RAM is not capable of executing this big batch, you'll see that you will be going out of memory all the time. So what you need to do is you know the size of your RAM, and then you reduce the batch size in case where the model is not running. So instead of 64, you may say 32. Instead of 32, you may say 8 or 16 or 8 or 4 or 2 or even 1. So, and batch size, as we know, is better like you choose a multiple of 2, or is it exponential of 2? So at each inner iteration, we have 64 batch of 1, and this is the dimension of individual image. So 3 by 32 by, so at 64 batch. So if you give in there, you see you will have batch size 64, and then you squash all of the rest. So it's 64 times 3072. So, and you will have your training for this 100 epochs. So we see that the loss decreases somehow, but we have no idea whether it is low enough. So in here, what we do is we calculate the number of correct divided by the number of total, so that we can calculate the percentage of correct that it. So this is just like a kind of evaluation. So for we touch.no grad, meaning since we are doing evaluation, we said we don't need grad, but in others we said we need to specify the required grad is equal to true, since we need a graph to be plotted. But here touch.no grad, so we don't need any graph to be plotted. For images and labels in validation loader, and validation loader, as we see here, we load our data set, which is CIFAR2 validation, batch size is 64, and we are not shuffling, as we see here. In training, we need shuffling, but in here, we don't require shuffling because we are not training. So batch size is equal to image.shape. We all know what it means. The output is, we fit our data set. And then prediction is touch.max, the output at dimension 1. So you are finding the maximum of the 2 probabilities. So you find the total, meaning whenever the output or the dimension 1. And what do we mean by the dimension 1? Our label. So yeah, so the maximum between the label and the output. So whenever we have label.shape, let's label. Yeah, label is in the validation loader. So we add all of the where the labels are indicates that it's correct. We predict. Sorry, when prediction is equal to label, we convert it into integer and we sum them together, so that we find all the instances where all of the where the prediction is correct. So we calculate them. And here the total represents the total data set that you have. So, and the accuracy here is 79.4. So, and it's very good, but not as good as we wanted, because they said on this data set, which now is not even in use, the accuracy is as high as 99.9 something. So, but in this small model, we already have 79. So the next one is to determine whether increasing the number of layers will lead to increasing the performance. So what you do is you experiment with more layers. So the first one that we see is just 3072, then 512, then 2. That's just what we checked. But here you can add more layers by this is the input layer, then the next hidden layer, and then the output layer. And at each you use the tanh as iteration function. And then at the last one, you use the log softmax as we've seen as the output. So the combination of log softmax and NN loss is equivalent to NN.cross entropy loss. So instead of saying given log softmax and then calculating your loss using N.LL, you can remove this log softmax from the definition of your model. And when calculating your loss, you can just say NN.cross entropy loss. So it does, it changes the output that you will get, and also it will calculate the loss using the negative log likelihood loss. So note that the numbers will be exactly the same as with the log of softmax and NN loss. So it's quite common to drop the last layer from the network and use this as the loss. So let's try that and try that and So most of the experiments, I think you can run them to find out how they work. We are running out of time. And this model accurately validation set. So yeah, these are methods that you just want to ensure that your model is the accuracy of your model is going up. So, and here you track the number of parameters that you are having. So in here you see your parameters depend on the size of the network that you define. It depends on the size of the input too that you are passing to. So you see there we are passing an input of 3072. So and at each layer and at the next layer we have the hidden size of 512, and then the next layer we have 2. So you are multiplying all of those by those numbers to find the number of parameters, number of trainable parameters in your model. So you can tweak those settings to reduce the number of parameters, trainable parameters, and you can reach to find some of this. It's self-explanatory. So in here, it gives the foundation of learning convolutional neural network instead of just going with this flattened linear model as an input. So in here, we are trying to provide. So as I explained there, if you have this image and we set all of the images, all of the pixels are contagious. So this first image is supposed to have a relation with this, and this. So that if, let's say we have an image here in the first instance here, we have our bed, it appears only here. So how about if the bed shifts to this place? So using this type of model that we are training, the model will not know exactly what this means. It doesn't give the room for shifting, because it doesn't know that this model, this pixel is related to this, and it's easily an object in this can shift to this, and then shift to this, and shift to this. So in so if you flatten it, this first one is first one, then 1, 2, 3, then the next one, which is this yellow. So is this yellow and this fourth one, they have a relation. But in this flattened list, it doesn't show any form of relation between the two. So, and they are non-contagious. So yeah, so what they give here is, if you pass in this, you have 1, 1, 1, 1. This is where your aeroplane appears in this image. and you flatten it and you give, and your model knows here this is 5 because it appears 5 in this place. But if this same thing shifts to this place, so if you flatten it, it might tell you that this is a different place and it is 1, because there is no any relation between all of this contiguous cell. So if one cell shifts, it's expected that the element in the subsequent cells that have a relationship will also shift together. So, and we'll see that in next chapter, convolutional neural network. So to conclude this, sorry for taking much of your time and for talking non-stop, and sorry for everything. So in this chapter, we solved a simple classification problem from data set, loading the data set, creating the model, minimizing the appropriate loss in the training loop. All of this will be standard tools for your Pytorch, and the skill needed to use them will be useful throughout your Pytorch tenure and the rest. So we've also found severe shortcoming for our model. We've been treating 2-dimensional image as 1-dimensional data because it's 2-dimensional really, but we are flattening it out to become only 1 dimension. Also, we do not have a natural way to incorporate the translation invariance in our problem. In the next chapter, you will learn how to exploit 2D nature of image to get better result. So if you see here, we are doing this using convolutional neural network. So we could also use what we have learned right away to process data without translating invariance. For example, using it on a tabular data or using time series, as we saw in chapter 4, we can probably do great things already. So to some extent, it will be possible if we use it on text data and the rest. So, and this is the summary. So this is the end of the presentation. Do we have anything in the question or adding some information and the rest?
Thank you, Dr. Idris, for taking us through this long ride.
Yeah.
Anyone with question? We are way out of the hour. I'm sorry for taking our time today. So anyone with question or addition?
I think we are getting up almost 2 hours here.
Yeah. Yeah. So anyone with question?
So for this thing, we introduce and we